Hey everyone! Today we want to talk about time-frequency domain representation in the world of audio. We will learn why time-frequency domain representation is preferable over time domain representation, what the short-time Fourier transform is all about, and its most important parameters. Let's start with a typical problem in speech processing, the suppression of a noise signal. Hey, do you want to learn about time-frequency domain representation?
Hey, what did you just say?
So what just happened here? The right ear had difficulties understanding the question, as our little noise source on the bottom left was walking over and singing. Here our main goal is surely the suppression of the singing voice of our little noise source, such that the two ears can understand each other. To find algorithms that can solve such a problem, we rely on a formal mathematical description of the scene. The signals can be either expressed in time domain, frequency domain, or by a combination of both. Let's look at the scene in more detail and name the different sources. Let x of t be the source signal we would like to keep, and v of t the noise signal we want to suppress. The signal that reaches our receiver, in this case the ear on the right, can be expressed as a simple addition of the source and the noise signal. All the signals are now expressed and shown in time domain, so simple amplitude or air pressure variations over time. However, there are multiple reasons why we do not want to process our signals in time domain, but rather transform them into time-frequency domain. Before we go into detail about how exactly this is done, let's see why this is beneficial to do at all. Our representation on the right side, in the time-frequency domain, is called a spectrogram, with time shown on the x-axis and frequencies displayed on the y-axis. The different colors indicate the amplitude of a particular frequency at a particular time. And this brings us to the first advantage time-frequency domain representation has over usual representations in time domain. The yellow-colored bins, the time-frequency bins that have a significant amplitude, are only a small proportion. That is to say that many audio signals are sparse in time-frequency domain. Usually a sparse representation is helpful, as fewer values need to be stored or encoded. In speech enhancement, there is another advantage. The noise or other disturbing signal is typically not represented by the same coefficients as the source signal. Let's take another signal and compare the spectrograms to each other. Sparsity leads to the phenomenon that there's only a small probability that both sources are active in the same time-frequency bin. Thus, there's only one source with a significant amplitude in each time-frequency bin. The spectrogram on the right shows the predominant source in each time-frequency bin, encoded by color. This phenomenon is called W-disjoint orthogonality. To understand why this is the foundation for many speech enhancement and classification methods, we'll take a look at another type of signal. We compare the two spectrograms of independent noise-like signals. You can see that those are usually not sparse in time-frequency domain compared to the speech signals above. Now we again predict the predominant source for each time-frequency bin. However, this is more difficult in this case. Both sources hold significant amplitude values in the same time-frequency bin, resulting in the more chaotic-looking spectrogram on the bottom right side. Therefore, we can tell that those two sources do not fulfill W-disjoint orthogonality. From now on, whenever someone refers to the sparsity of the sources, you'll exactly know what they are talking about. Another reason for time-frequency domain representations is that natural sounds often have a structure in both time and frequency. The structure of the noise and the speech signal may consist of different characteristics that make them unique. Take, for example, a harmonic sound that usually corresponds to horizontal structures in a spectrogram, whereas noise-like sounds, such as applause or distorted guitar, lead to many Fourier coefficients distributed over the spectrogram without any clear structure. Those characteristics can be used to differentiate sources from each other or improve the estimation of individual source statistics. The last reason I'd like to mention here is that most source separation and speech enhancement methods apply a time-varying filter to the mixture signal. This filtering process is usually expensive, as it requires a convolution operation in the time domain. We know, though, that time domain convolution can be implemented as complex valued multiplication in the time frequency domain. By transforming the signal, we can avoid the expensive convolution operation. Okay, so let's summarize the advantages of processing signals in the time frequency domain. We saw that natural sounds are often sparse and have a prominent structure in the time frequency domain. Moreover, it is often required to filter in some sound sources, which can be easily modeled in time frequency domain. So how do we come up with a representation in the time frequency domain? In practice, the short-time Fourier transform is often used. We start with a signal in time domain. We then cut the signal into shorter segments and transform each of them into the frequency domain. In the last step, we combine all the segments to come up with a time frequency domain representation, the spectrogram. Let's take a closer look. We start again with the signal in time domain. We create a series of overlapping windows, which is as long as our signal in the time domain. Multiplying the signal with those windows leaves us with shaped signal segments. Here we used overlapping Han windows. Han windows are one of the commonly used windows in spectral analysis. However, there are many more that can be used for the analysis, and depending on your aim and application, it is highly recommended to try out different ones. Let's get back to our STFT and apply the Fourier transform on each of those windowed signals. I'm pretty sure you have heard about the Fourier transform, and probably you're like, oh no, not again. But let's try to get an intuitive understanding of the Fourier transform. Remember the spectrogram representation? It had the time on the x and the frequencies on the y-axis. Our overall goal is to get a description of frequencies that are present in our time segments. Keep that in mind as we move on. The simplest sound to analyze mathematically is the pure tone, one where the pressure variation is described by a single frequency. A pure tone would look like a sine curve. Imagine the sine wave makes 440 oscillations a second. That would mean that the wave has a frequency of 440 Hz. However, pure tones are rare in nature, and usually natural sounds consist of a combination of multiple frequencies. So let's add some more pure tones. You can see how the pressure wave changes the more pure tones we add. This now looks more like a pressure wave that could have been captured by a microphone. You may also notice that this looks similar to the pressure wave of the harmonic sound we've talked about before. And really, a harmonic sound is nothing else but a combination of related frequencies. So what the FFT block really does is decomposing our signal into all those pure tones consisting of only one frequency. Imagine you did not know about the Fourier transform. Can you think of a way to find the frequency of a specific sound? Let's take a graph with, let's say, 5 beats per second and some fixed length. If we did not know the frequency of that signal, how could we possibly measure it? Let's start by wrapping this graph around a circle. The lower points of the graph will be close to the origin, while higher points correspond to a greater distance from the origin. Depending on the length of the graph, we might need more than one round to wrap the signal around our circle. It's important to notice that the velocity of our vector wrapping the graph around the circle is different from the frequency of the signal, so to say the 5 beats per second. To come up with this other pattern, we only change the wrapping velocity from 0.5 cycles per second to 0.79 cycles per second. Looks cool, right? But how does that help us in any way to find the frequency of our signal? Imagine the circular plane to be some kind of tray, and our graph would have some kind of mass that is lying on top of it. Surely this object would have a center of mass, indicated by the red dot here. Depending on the pattern of our graph, the center is likely to shift. To see if this is true, we are going to increase the cycling frequency and see how our center of mass changes its position. We are only going to plot the x-coordinate of our center of mass here. The frequency on the x-axis now corresponds to the frequency we use to wrap the graph around the circle. We start with 0 cycles per second and slowly increase the frequency up to 9 cycles per second. Not a lot is happening here. It seems that our center of mass mostly stays in the center of the circular plane. Our tray is not likely to tip over. But wait! There, around 5 cycles per second, our graph sums up and you can see that the center of mass moves downwards. This came somewhat unexpected. It means that the position of our center of mass changes only significantly whenever our cycling frequency matches the frequency of our graph, the 5 beats per second. However, for all of you who have seen a frequency spectrum before, that doesn't quite look like one, right? Remember though, that we are only plotting the x-coordinate of our center of mass. One part that we are missing out is that the center of mass is not only defined by the x-coordinate, but also by the y-coordinate. And whenever we are dealing with the two-dimensional plane, we can also think of it as the complex plane, where the center of mass is defined by a real and an imaginary part. We can describe every point on our graph pattern by a complex number, and thus we won't lose any information. Let's recap a bit of complex number theory here. Instead of using the real and imaginary part, we can think of polar coordinates. There we use the distance to the point and the angle between the positive real axis and the vector pointing from the center to our point. Maybe you recognize this as the one part of Euler's formula. And you can describe any point on the unit circle by walking theta units around a circle with radius 1, counterclockwise, starting on the right. And hey, doesn't that look somewhat like our vector painting the graph on the circular plane? If we were to describe a rotation of 1 cycle per second, we could take the expression e to the power of I times 2 pi times t. 2 pi corresponds to the circumference for a circle of radius 1, and t is the amount of time that has passed. Now if we want to cycle with a different frequency, we could simply multiply the time t in the exponent by the frequency f. Suppose we set f to 1/5. In this case, our vector makes one full turn every 5 seconds instead of one full turn each second. If we now think in terms of the Fourier convention, we would rather rotate in a clockwise direction, and therefore we multiply the exponent by a -1. However, what we like to see is how our graph gets wrapped around the circle. So let's take our cosine wave from before and call it g of t. If we now multiply g of t with our exponential expression, it means that our vector gets scaled up and down depending on the shape of our function g of t. Just think of this as the r in the description of a polar coordinate to describe any complex number on the plane. This is awesome! This formula summarizes our whole idea of winding up a graph. And now we are only one step away from finding the frequency of our graph. What is left now is how to capture the center of mass. A good approximation might be to sample a whole bunch of points from the original signal, find their position on the winded graph, and average over them. And that's it. What we just derived is the formula of the discrete Fourier transform. And as we are usually working with digitized audio signals, this is completely sufficient for now. There is a nice way to summarize all the components of the formula in one sentence. We are interested in the energy at a particular frequency that can be calculated by spinning our signal backwards around a circle at that frequency and averaging a bunch of points along that path. The important thing here to note is that the output of the Fourier transform is a complex number. However, we are usually bad at giving a complex number any physical significance. For interpretation, this representation is not particularly useful. Even more, remember that our whole idea was to end up with a spectrogram displaying frequencies over time. How can we plot a complex number to directly see by which frequencies our signal is determined? Let's try to break those parts apart, the real and the imaginary part, and see what they tell us about the signal. Once more, let's look at the complex plane and derive Euler's formula as a whole. It enables us to convert between Cartesian and polar coordinates. While the real part is given by the cosine of theta, the imaginary part is given by the sine of theta. All we do here is to describe the two side lengths of an angle by the use of trigonometric functions. We can apply the same concept to describe e to the power of -I theta by throwing in a minus sign. Now let's rewrite our formula. We transferred back from polar coordinates to a description by a real and an imaginary part. But how does that help to give any physical significance to it? Maybe a plot can help. Let's take a new graph, g of t, and plot the real part, given by the average of g of t times cosine, and the imaginary part, given by the negative average of g of t times sine. Stop here for a moment. Could you tell how many pure sounds were added up to construct the graph on the left, and what are their frequencies? If you were to give a random guess, it would probably be something like 2 pure sounds, one with a frequency of 2 Hz and another one with a frequency of 3 Hz. Can we do better here? Let's take the square of both of them, add the real and the imaginary part up, and norm this whole thing, so that it nicely fits the screen. And yeah, that's it. One could clearly state that a sound of frequency of 2 Hz and 3 Hz influences our composed signal significantly. What we just plotted is called the amplitude, or the absolute magnitude of the graph. However, it seems like we lost something in this representation. Knowing only the amplitude of the graph, could you easily go back and plot again the real and the imaginary part? We cannot reverse the summation of the real and the imaginary part if we know neither one of them. But we can describe any complex number by the distance to the origin and the angle between the positive real axis and the vector pointing from the origin to the number. Think of the distance in terms of the plotted amplitude. If we were able to compute the angle using the real and the imaginary part, we would have again a complete representation of our signal. We won't go into detail here, but in general, we can look at the amplitude and the phase spectrum to get a complete representation of our signal. For the spectrogram, it is sufficient to look at the amplitude spectrum of the signal, as for now, we are only interested in the predominant frequencies in a particular time bin. Remember the FFT block? We came a long way from when it first showed up here. But now we are done. We started with the idea that we can decompose any sound into multiple pure sounds with different frequencies. We then use different cycling frequencies to wrap our signal around a circle. Most importantly, we recognized that our cycling frequency matches the frequency of our signal whenever the position of our center of mass moves significantly. From there, we derive the formula of the discrete Fourier transform, leaving us with the energy at a particular frequency, given as a complex number. In the last step, we found that we can compute the amplitude spectrum by squaring and summing the real and imaginary part of our discrete Fourier transform. So let's go back to the STFT overview. We were about to apply the FFT on our windowed signals. I'm sure you can now easily interpret the amplitude spectra for each of those windowed signals. There's one problem left here. For better visualization, we used a signal length of 1 second, resulting in windows of 200 milliseconds. However, in speech processing, we usually use shorter windows due to the non-stationarity of our signal. Let's look at only 128 milliseconds, such that our windows result in a length of 32 milliseconds, a common length for speech analysis. Okay, great. But how do we get from the amplitude spectrum to our spectrogram? Simplified, imagine turning each amplitude spectrum by 90 degrees, such that the frequencies are displayed on the y-axis, and encode each amplitude value by color. In the last step, we combine all the time frequency bins to come up with the spectrogram for the whole signal. From this overview, you could already envision that there might be many parameters to be adjusted depending on your kind of analysis and application. Think of what is adjustable in this diagram. First, there are the FFT blocks, where you could adjust parameters. Secondly, there's the window function, which kind of came out of nowhere. We won't look into the FFT parameters today, but rather see how the spectrogram changes depending on the window function. The window function is characterized by their shape mainly. We chose a Hahn window, but of course there are many other shapes you can choose from, which come with advantages and disadvantages. Another thing one could adjust is the window length. You can choose shorter windows or longer windows. This will heavily influence your spectrogram's resolution. One last thing we could think of, if creating a series of overlapping windows, is of course the overlap itself. As you can already see from the two graphs shown here, the overlap has an influence on the number of windows you would need to analyze your audio signal if the window length stays the same. For now, we will stay with the Hahn-shaped window and check in which way window length and overlap influence the analysis. Let's start with the window length and see how it influences the look of our spectrogram. The window length determines whether your spectrogram results in a high time resolution and low frequency resolution, or vice versa. You will never be able to achieve both a high time and high frequency resolution. Therefore, how you choose the window length will highly depend on your application and what you want to detect in your signal. Let's look at an example. We constructed a signal consisting of two sine waves with a frequency of 400 and 450 Hz and added two impulses. The whole signal has a length of 500 milliseconds. We can now analyze the signal using two Hahn windows of different length. One short one, only 32 milliseconds long, and one longer one, 128 milliseconds long. How will the spectrograms look like? On the left, we can see how the short window divides the signal into shorter segments without overlap. This results in a spectrogram in which the two impulses are clearly separated, however, we cannot distinguish the frequencies of our two sine waves. Let's see what happens if we use the longer window. On the left side, we can see that we only need roughly 4 windows to analyze the whole signal. And here we can clearly separate the two sine waves, but the two impulses are not visible anymore. What you can see from the two spectrograms is what we call the time-frequency trade-off. Let us now take a closer look at the overlap parameter and why it is important to consider. Remember that we multiply the signal we want to analyze by a series of windows. Here we start by looking at non-overlapping windows. The weight close to the boundaries of a single window function is typically very small or even 0. By multiplying the signal with the window function, we are effectively ignoring the data in those areas. Thus, our analysis will be incomplete. This is clearly not optimal, as we want to extract as much information as possible. We can improve this by letting the segments overlap. In such a case, our weight is not equal to 0 anymore. Therefore, we won't lose any parts of the original signal during the analysis. So overlap is great, but how much do the window functions actually need to overlap? Similar to the window length, we need to find a trade-off here. However, this time, a trade-off between the resulting flatness of the data weighting and the computational effort. Remember that the more our windows overlap, the more windows we need in total to analyze the whole signal. This results in a higher computational effort. But what do we mean by the flatness of data weighting? Let's look at an example. We have a series of overlapping windows with an overlap of 33%. By multiplying the speech signal with the series, we weigh every data point of our speech signal, depending on where it hits the series of windows. One possible measure of the total weight of each data point could be the sum of all window values applied to this data point. As we want to analyze an unknown signal, we would like to keep the weighting the same for each data point in the signal. Therefore, we want to keep the sum of the window values, so to say the blue line in our plot, fairly constant. In this case, however, we can clearly see that it is not constant, and calculating the amplitude flatness results in a value of 0.5. The flatness measure results in a value between 0 and 1, with 0 being the least flat and 1 being the optimum possible outcome. Let's see what happens if we move the individual window functions closer together. If we now check for a 50% overlap, we can clearly see that this results in a flat weighting function. So whenever we are using a Hun window of variable length, a 50% overlap will result in an optimum weighting. This is commonly used in speech and audio processing. So in case you want to start your signal analysis right away, remember how the different window function parameters could influence your analysis, and try to play around with them. For a standard procedure, you can choose a Hun window with a 50% overlap and try out different window lengths. Always remember that the window length determines your time and frequency resolution, and that you have to decide which one is more important to you. Congrats! You've made it to the end of the video. You're now ready to go out and explore all kinds of signals in the time-frequency domain. Today you've learned why it is useful to process signals in time-frequency domain and about the short-time Fourier transform. We covered all the steps from the time domain signal to the spectrogram, the representation in the time-frequency domain. You hopefully got a more intuitive understanding of what the Fourier transform is about and how we can find the predominant frequencies in our signal segments. Lastly, we looked at the window function, its most important parameters, and their influence on the short-time Fourier transform. We covered a lot in today's video, but there's so much more to discover in the world of audio. See you soon as we continue our journey.